So that finishes our research, our investigation of analytic reconstruction formulas for the radon transform. But there's one more aspect which I would like to mention and which will lead us to what we're going to do next week. I already told you that the parallel geometry which we looked at and for which we derived the inversion formulas were actually a simplification. That's not the real thing. What really happens is very close to what we looked at in the 3D case. That's the so-called fan beam measurement. We have, for every fixed position of the source curve, for every fixed position of the source, of the X-ray source, we can measure, also in the two-dimensional case, the lines that start at this point over here. So even if we just look at the two-dimensional case, then the kind of measurements that we have is we can measure all the lines that start over here and then go through the body. This is definitely not what we described as parallel geometry. That's only true if that point over here is infinitely far away. So by face value, our recon algorithm that we derived simply doesn't work here. Now, what can we do? Well, we can now derive a special reconstruction algorithm for this geometry, which is possible and which can be done. Or we can use the second alternative. We can just use interpolation to map the measurements that we have onto a parallel geometry and then do our analytic reconstruction from that. However, we have the feeling that it's not very nice that it was actually a coincidence that we could come up with a reconstruction algorithm for parallel geometry and also coming up with a reconstruction algorithm for this one here. An analytic reconstruction algorithm for this one isn't too easy as well. So this gives us a lot of restrictions, right? I mean, it could be that from some directions we just cannot measure in a given tomograph, and so we'd be completely lost, right? We need all the measurements for our reconstruction algorithm, and so if there's something missing, then we can't do anything with that. Also, if anything is non-equispaced, we won't be able to tackle that using our analytical algorithms. So that's not good. I'm going to introduce you to a new idea, which is so simple that you probably won't believe it. So the idea simply is, well, we finally want to compute an image, and that image has a finite resolution. So let's, for simplicity, assume that all we want to compute is an image of size, well, 3 by 3. It should be typical is about 1024 times 1024, but let's leave it at 3 times 3. So this should be a 3 times 3 image. This is the reconstruction area over here. And of course, that image consists of 9 pixels. And in each pixel, we have values from F1 to F9. Okay, so our assumption is that we have an image that is the function f that we reconstruct is constant, equal to f1 in this pixel over here, equal to f2 over here, equal to f3 over here, and so on. Now, we have made measurements, and let's take the measurement line L1 over here. So we've measured the integral over L along this line. Okay, and the result was G1. So integral over L1, f of x dx is G1. Now, if this is a reasonable approximation to our function f, then also the integral over L over this discrete thing over here should be equal to G1. But that's now easily computed because the approximation is constant along in this part over here, and the length of the line over here is 1 1/3. Let's call it h. So the contribution to the line integral of this pixel over here is something like f1 times h. Same thing here, the intersection between L1 and this pixel is, again, the length is again h. So contribution of this pixel to the line integral is h times f2, and it's h times f3 over here. And all the contributions should add up to the measurements. So we would assume that h times f1 plus h times f2 plus h times f3 should be equal to g1. Okay, but we can do that for any line, right? So we would assume that the sum of the contributions of each pixel to the line integral times the value of the picture in that pixel fp should sum up to the measurement that we had. So we get something like the sum over all p akp times fp is gk, where akp is the length of the intersection of the line with the pixel. And again, this is just the contribution of the pixel p to the line integral along lk. Okay, so that's pretty straightforward. But now this is just a linear equation, right? So we can write it as a matrix vector equation. And so putting A equals to AKP, G equal G as the vector of all measurements, F the vector of all pixel values. Then we have the matrix vector equation AF equals G. Simple matrix equation, which we can solve for A, or maybe we'll have to take the least square solution or something. But anyway, we can solve it. And we get an approximation of F, which discretely satisfies our measurements, which sounds great. Okay, so this is completely independent of any geometrical considerations. You can measure along any lines you like, and still this algorithm is going to work. Okay, that's great. And probably it's going to be a little bit slow because that matrix is probably going to be pretty large. As I said, usually you have image size of something like 1000 times 1000. So these are 1 million unknowns and several million values, several million measurements. So this is quite some size. But nevertheless, we might be able to solve this equation iteratively, and that's exactly what we'll do next week.